The last time I was with you, we talked about differential equations that model growth or decay in a population or in a situation, and we learned how to solve those. So, touching back on that, if the rate of growth of a population is proportional to the population, we know that we can set up dp dt is equal to k times the population, where k is our constant of proportionality. And if we solve for p, we would get p is equal to c e to the kt, where c is some constant and k is some constant. So that is called the exponential growth equation, and the population would continue to grow if k is positive forever. So the limit as time goes to infinity of the population would be infinity in an exponential growth equation. In reality, though, the growth of population rarely ever continues forever. There is some maximum possible size due to various reasons. So a logistic growth equation includes that limiting factor, that carrying capacity. Logistic here means reasoning or logical, not logarithmic, FYI. Logistic differential equations do not have a meaning, an underlying meaning of logarithms. We might get a log, but that's just part of solving the equation. It has nothing to do with the terminology for these. Okay, the maximum p-value in a logistic differential equation is called the carrying capacity, or the limiting value. Okay, you might see the variable c or L representing that carrying capacity. Okay, in every logistic equation, P grows at a rate proportional to itself and that carrying capacity minus the population. So that is the room for growth. So every logistic differential equation is going to be able to be written in this form. Able to be written in that form. Okay? The limit as time goes to infinity of the population is L. Couple of things about this equation I want you to take note of. I need you to recognize this as a logistic differential equation. One way to recognize it is whatever variable is up here must be here and here. Okay, you can think of it as the McDonald's Golden Arches, the McDonald's, or you can think of it as Mrs. Murray. Regardless, I need you to remember that. And there are no T's over here. Okay? The other thing that has to be there is that has to be a minus. It has to be that's going to create that room for growth. Okay? So I need you to be able to recognize that. Okay, I have seen AP multiple choice questions where they give you 4 or 5 equations, differential equations, and they simply ask which of the following is logistic. So these are the things that you're looking for. Okay. All right. Every logistic differential equation has 3 possible solution curves. Every one does. So this is key to this section. I want you to be able to very quickly draw the graph. Okay? And it's very easy. Okay? This L value here is going to be a number. Whatever that L value is, that goes on the graph first. Okay? That is going to be your horizontal asymptote. That is your carrying capacity, your limiting value. That is the limit as time goes to infinity. So that is going to be a horizontal asymptote. And as time goes to infinity, that's where our curve, all our 3 possible curves are going to end up. Okay? The next thing that you will always put on your graph is the value that is 1/2 of this L. Whatever it is, whatever L is, 1/2 of it is going to go on that curve. Okay? All right. So that is the basic. That will be on every one of these curves when you graph it, and it's key to graph it, to answer the questions that you're going to be asked, is to know what this graph looks like. Know what the 3 possible solution curves are, but know this outline of the graph. All right. The first situation occurs when our initial population, you will be given your initial population. So you're going to be given a value that goes right here on your population axis. This is our population axis. This is our time axis. So let's say that our initial population is somewhere below 1/2 of L. Let's put it down here. Whatever that is, it's down, they give it to us, and it's below 1/2 of L. If it is, then our curve is going to look like this. Think about this. We start here. Our curve is going to be, it's going to go up quickly. It's going to, well, it starts out real gradual, but it goes up, it's concave up, until the population is this 1/2 of L. After it's the 1/2 of L, it does that. It's concave down. And it gets very, very, very close to L. This is a point of inflection in the population curve. Okay? The next possibility is if our initial population is somewhere between 1/2 L and L. Okay? Let's say it's right here. Somewhere between 1/2 L and L. If that's the case, you do not have this gradual concave up piece. The entire thing is concave down, and it does that. So it too approaches this horizontal asymptote, but it looks like that. No point of inflection, no change in concavity. That's all we have. The third possibility of a solution curve is if the initial population is above this L value. If it starts above the L value, then you're going to have, we want our end behavior to be this L, this horizontal asymptote. There is no change in concavity. This whole thing just is always concave up, and it does that. So again, it gets extremely close to this horizontal asymptote. Okay? So those are the 3 different possibilities for solution curves. And they all depend on where we start. Where do we start? Okay, let's look at an example. Let's consider a fish pond for which the rate of population growth is modeled by this differential equation. First of all, I know they didn't tell me it was logistic, but I know it's logistic because of the form of it. P, P, and P, and a minus. We can make this be in this form, and that's always key to do. First, make sure your differential equation is in this form, then graph. Okay? All right, so first let's get it in the right form. So I'm going to notice that there's a P outside of the parentheses. I'm going to begin by factoring out a P. So dP dt will equal, I'm going to take a P out. I'm going to be left with 3 from the first term, and from the second term I'm going to just have a P taken out. I'm going to write this as 1 over 600 P, just because after teaching this I know that helps kids. Okay, so I'm just moving this 1 over 600 outside. Okay, now we're a little closer to this. but notice that in this form, this P does not have a coefficient other than 1. The coefficient has to be a 1 on that last P. Right now the coefficient is not 1, it's 1 over 600. So we need to factor the 1 over 600 out as well. So I'm factoring out 1 over 600. Okay? That's going to be this K value here. Alright? Okay. When you factor out 1 over 600, what is left from the 3? Well, when you factor out 1 over 600, you're dividing 3 by 1 over 600. And 3 divided by 1 over 600 is 1800. If you multiply this back in, you should get 3, and we do. 1 over 600 times 1800 is indeed 3. Okay? And then over here we'll just have P. And now it's in the form we need it to be in. It's in this form. We need it to be in this form because we want to see what L is. And L here is 1800. So when we graph this, and we always want to graph these, when I graph it, I know my L value. L is right here, and it's 1800. That is my horizontal asymptote. Excuse me, it's my end behavior, horizontal asymptote. Another key number is always 1/2 of L. Well, half of L here is 900. Okay? Now, to graph a solution curve, we need to know the initial population. Gosh, that startled me. We need to know the initial population. Well, the initial population here at time 0, there are 500 fish in this pond. So I'm going to come down and graph it. Well, 500, it falls below 900. So I know what the population curve looks like. In general, I know what it looks like. It's concave up, and then it's concave down the rest of the way, with a point of inflection right at population of 900. Couple things here, okay? First of all, notice that there are no hash marks on the t-axis. You will never have hash marks on your t-axis, okay? To know anything about time, anything specific about time, we would have to solve this differential equation, and it gets pretty messy. You're not going to be asked to do that in this course. All right. So just get used to that. Your time axis will be empty. All of the business is going to go on the p-axis, your population axis. Okay. All right. Let's answer these questions. What is the limit as time goes to infinity of our population curve? This, what we drew, is the population curve. All right. So we want to know what is, as time goes to infinity, what is P? Well, as time goes to infinity, P is going to be approaching this 1800. Okay. So this is going to be 1800. They did not ask for units. If they did ask for units, the units would be fish in this case, because that's the units for P. All right. For what values of P is the population of fish increasing? Well, the population is increasing forever, right? So for what values of P is the population increasing? Well, population is increasing from 500 up to 1800. So I'm going to write that down. It's increasing from 500 to 1800 fish. Technically, we include the 500. We do not, because increasing, decreasing, you include boundaries if they are part of your range. 500 is part of our range, so we include it. We're not going to include the 1800 though, because according to this model, we will never reach the 1800. So this is when these are the p-values when the population is increasing. For what values of P is the population increasing at an increasing rate? Well, the population is increasing here. When is it increasing at an increasing rate? That would be when our population is concave up. Okay, increasing at an increasing rate would be when the curve is concave up. So that's this section here. So from 500 to 900, and for concavity we do not include endpoints ever. Okay. For what values of P is the population increasing at a decreasing rate? Well, that's going to be when we're increasing but concave down. So that's going to be from 900 up to 1800. Okay, what is the population of fish when the population is increasing the fastest? Okay, well, the population is increasing the fastest when we're increasing the fastest, the highest, right? So this is going to be when the slope of the tangent line is at its highest number. So think of tangent lines here. Think of tangent lines. This tangent line has a small slope. This tangent line has a steeper slope, a higher slope. This is higher, this is higher. The tangent line gets steeper and steeper and steeper and steeper until we get to this 900, and then what happens to the tangent line? Well, it starts to go, the slope now is decreasing. Here the slope is increasing. Here the slope is decreasing. The slope is still positive. It's just it's increasing and then decreasing. So it's highest when the population is right here at 900. We know nothing about time. I have no idea what time that is, but we know it's when P is 900. So what is the population of fish? The population of fish is 900 when the population is increasing the fastest. Okay, part F. What is the rate of growth of the population when the population is increasing the fastest? And we have to indicate units. What is the rate of growth of the population when the population is increasing the fastest? So they're asking us what is dP dt when the population is that 900. Okay, so I'm going to go back into any of my dP dt equations and plug in 900 for P. So I can go into the original equation, I can go into this equation or this equation. It doesn't matter at all. I'm just going to go into my last equation. 1 over 600 times P times 1800 minus 900. I almost wrote P again. Okay, and that's a safe stop spot. I'm going to indicate units. The units will be units for P divided by units of T. So that's going to be fish per year. That would be my safe stop spot. If it was a multiple choice answer, we would need to simplify a little bit. 900 over 600 is 3/2. 1800 minus 900 is 900. That's 3 times 450, which is, let's see, 1350 fish per year. Okay, that would be if it was a multiple choice question. If it's not multiple choice, you leave it right there. Okay? All right, let's look at another example. Let's consider a lake. Let's consider a lake for which the population growth rate for a certain fish is given by this differential equation. Okay, is it logistic? Yes, it is. I see a P, there's another P, there's another P, there's a minus. Yes, it's logistic. Okay? No T's, only P's. Okay, P is the fish population, T is in years. Okay, at time 0 years, there are 60,000 fish in the lake. Okay, well this is logistic, but it's not in the form that we need it to be in yet. Remember that we need it to be in this form. dP dt is equal to Kp times L minus P. It is almost in that form, but the coefficient for this P has got to be a -1, and right now it's -1 over 75,000. So we're going to do just a little work to get it in the right form. Okay, this 5 over 21, I'm just going to leave it out there, and I'm just going to rewrite this as 1 minus 1 over 75,000 P. And now I'm factoring out this 1 over 75,000, so I'm going to have 5 over 21 times 75,000. I'm not going to bother simplifying that at all because we really don't need to know that K value. It's sitting there, but we really don't need it. The only time we would need to worry about what this number is for K is if we were actually solving the differential equation, and I already told you we're not going to be doing that in this course. Okay, so now we're factoring out the 1 over 75,000, so this is going to be 1 divided by 1 over 75,000, which is 1 times 75,000. So now we know our L value. Okay, L is 75,000, so the graph is going to look like this. We have 75,000, half of 75,000. What's half of 75,000? Let's see, if I divide that by 2, I'm going to get a 3, carry the 1, so 7, one more, 37,500. Okay, and this is my horizontal asymptote every time in logistic. So I have that, and my initial value of P. When time is 0, there are 60,000 fish. So we're in between L and 1/2 of L at 60,000 fish. So I know what the graph of this looks like. The graph is always concave down, and it does that. Okay, I could prove that to you. We could do a lot of work to get that, but it is absolutely true. This is how I want you to do these problems. Okay, all right, let's go through these questions. What is the limit as time goes to infinity of P? Well, as time goes to infinity, the limit is 75,000. Didn't ask for units. If they asked for units, it would be fish. For what values of P is the population of fish increasing? Well, it's increasing from P is 60,000 to P is 75,000. So 60,000 to 75,000. Again, technically we include that 60,000. If you don't include it in a FRQ, you would still get full credit. For what values of P is the population increasing at an increasing rate? Okay, so when are we increasing and concave up? Never. Okay, no values of P. For what values of P is the population increasing at a decreasing rate? So increasing but concave down. That's all these values. So 60,000 to 75,000. And again, we don't include the boundaries for that question for concavity. What is the rate of growth? What is the rate of growth? So we're finding dp dt of the population when the population is increasing the fastest. Well, when is the population increasing the fastest here? When is the slope of the tangent line the highest? When is the tangent line the steepest? Well, the tangent line is steepest right at the beginning, right when we start, when time is 0, when the population is 60,000. So this is going to be dp dt when P is 60,000. Okay, so that will be, I'm going back into my dp dt equation, and I'm just using this last one, but we could use any of them that we want to. When P is 60,000, and then we have our limit minus 60,000, and I'm definitely not going to do any more simplification for that. I do need to indicate units, so this would be fish per, it's the units for P divided by units of T, and again this is in year. So that would be my safe stop spot, my final answer. One more example. A pond is created and it is known that catfish will have a population growth rate modeled by this differential equation. I can look at it and I know it's logistic. P, 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 no T's and a minus. It is definitely logistic, where T is measured in years. A supply of 7,000 catfish is put into the pond to initiate the population. Okay, so the first thing we need to do is get it in the right form. So we need to get it in this form. Okay, I begin by factoring out a P. So I'm going to factor out a P, and I'm left with 4/5 minus 1 over 8,000 P. Okay, now I need to make this coefficient a -1, so I'm going to factor out a 1 over 8,000. Okay, 4/5 divided by 1 over 8,000 will be 4 times 8,000 divided by 5. 4 times 8,000 divided by 5, so 32,000 divided by 5. Okay, so this is our L value, and L is 32,000 over 5. I'm going to do a little division here. 5 goes into 32 6 times with 2 left over. 5 goes into 24 times, and then we have 2 zeros. So L is 6,400. So on our graph, L is 6,400. Half of L is 3,200. But what is our initial value? The initial value is 7,000. So we have this pond, okay? This pond is known to hold a maximum of 6,400 catfish. And we throw 7,000 catfish in this little pond. What is going to happen to these catfish? What's going to happen? Well, they're going to die. They're going to die off because the pond cannot sustain them. There's not enough resources in the pond to sustain 7,000 fish. The maximum it can sustain is 6,400. So are these fish going to die slowly or quickly? They are going to die, and they're going to die fast, right? So this is going to look like the curve, the solution curve here is going to look like that. According to the model, The fish will never actually reach 6,400. They'll always be a little higher, but in reality, they would end up right there eventually. Okay? That's what the solution curve looks like. So what is the limit as time goes to infinity? It is the 6,400. They didn't ask for units. If they did, it would be in catfish. For what values of P is the population of fish increasing? Well, the population, according to this model, the population is never increasing. Okay? All right. What is the rate of growth of the population? What is the rate of growth? So we're looking for dp/dt again. When the population is decreasing the fastest. Decreasing the fastest. Well, we're decreasing the fastest right at the beginning, right when we start. So they are asking what is dp/dt when the population is 7,000. Remember, no time. There's nothing on the time axis. We know nothing about time. Okay, so P is 7,000. So I'm going to go into my differential equation, put 7,000 in for P. I can go into any of them, doesn't matter which one. I'm just going to go into the last one again. So 1 over 8,000 times P times that 6,400 minus 7,000. Indicate units. We are in catfish per year. Units of P divided by units of T. And that's it. That is logistic growth, and it is probably one of the easiest of our BC only topics. This is a BC only topic. AB will not get there. Okay?